Good evening, Sanibonani, goeienaand, Dumelang. My name is Kinta Burger and I'm the Registrar at the University of Johannesburg, and this evening it is my honor and privilege to welcome you on behalf of the Vice-Chancellor of the University to the Professorial Inauguration of Professor Kriveshini Pillay. A warm welcome to all of you, the family, friends and colleagues of Kriveshini, to this joyful and landmark moment. In particular, I would like to welcome Prof André Strydom, the Vice Dean of the Faculty of Science, but also our respondent this evening, Prof Neil Kovel, who's an Emeritus Professor at the University of Witwatersrand, next to us, Professor in Chemistry there. Also a warm welcome to all members of Senate and all other colleagues and guests who are joining us via our online platforms. Ladies and gentlemen, the inauguration of professors is a public ceremony in which a newly appointed professor is inducted into office and deliver the inaugural address. The ceremony of the inauguration of professors has its roots in the medieval university and serves multiple purposes. Firstly, it's an expression of welcome and an entry for new professors, joining the circle of colleagues who are already professors. Secondly, it provides a platform for the professors to display their expertise in the discipline and showcase their research. Thirdly, it stands out as a moment of pride and celebration for the incumbent, the family, fellow scholars, the university and society. In essence, it is a celebration on the achievement of major milestones, contributions to the discipline, and ultimately the impact on society. Today we will witness the entry of Professor Kriveshini Pillay to the illustrious community of scholars at the University of Johannesburg. This evening we will listen to Prof Pillay as one further step in the journey of being a professor. This is a journey which does not culminate once this lecture has been given. Rather, it's a self-reflective pause in the journey of the professor, with a promise of more to enrich our minds and simultaneously contributing to the rich intellectual body of work in the discipline. Prof Pillay, we are looking forward to your address. I now invite the Vice Dean, Professor André Strydom, to introduce Professor Pillay. I thank you, Rialiboga, Siyabonga, baie dankie.
Professor Kriveshini Pillay was born in Pietermaritzburg, KwaZulu-Natal in 1974. She attended high school at Ruysthorpe Secondary School and matriculated in 1992 with 4 distinctions. She obtained her BSc degree majoring in chemistry at the University of KwaZulu-Natal, formerly known as the University of Natal, on the Pietermaritzburg campus in 1996. She subsequently graduated with her BSc Honours in Chemistry at UKZN in 1997. She obtained a Master of Science in Applied Science degree in Chemical Engineering at the University of Cape Town in 2001 and a PhD in Chemistry at the University of the Witwatersrand in 2011. She joined Technikon Witwatersrand as a lecturer in chemistry on 1 July 2001 and is now 20 years in service at the University of Johannesburg. She is currently a full professor of analytical and environmental chemistry in the Department of Chemical Sciences at the University of Johannesburg. Her research interests are in developing nanomaterials for water treatment and forensic applications. She has to date hosted 4 postdoctoral research fellows and graduated 16 MSc students and 11 PhD students. She has published 53 journal articles in internationally accredited journals, 5 book chapters, 2 conference papers, and filed 1 patent. She has presented papers at 11 international conferences, has a Scopus H index of 23, Google Scholar H index of 25, and 1,788 citations. Professor Pillay served the Department of Chemical Sciences as Deputy Head of the Portfolio of Teaching and Learning for 3 years, and also represented this department on the Faculty of Science Teaching and Learning Committee and the Faculty Higher Degrees Committee. She has additionally served as a reviewer for several internationally accredited journals, as well as served on the review panels for the South African National Research Foundation and the Water Research Commission. I now invite Professor Pillay to deliver a lecture.
Thank you, Professor Stradom. Good evening, colleagues. Good evening to the online audience. A special greeting to my family members and friends who are watching this online. You haven't seen me for 2 years, and now you'll be seeing my face on a computer screen. I'm going to take you through my journey through professorship, and hopefully by the end of this evening, I will be able to convince you that nanotechnology is a powerful tool for solving South Africa's problems. So I'm going to start off with a bit of background telling you what nanotechnology is all about, where it all started. I'm going to go through some different kinds of nanomaterials and nanostructures that have been identified. Then I'm going to highlight some of my past and present research initiatives, and conclude with some insight as to where to take nanotechnology forward, especially as we enter the 4th Industrial Revolution regime. So many scientists like to call nanotechnology the science of the small. And the reason for this is because we are studying materials with nano-sized particles. And just to give you an idea of how small it actually is, 1 nanometer is 10 to the minus 9th of a meter. So these particles are so tiny you cannot see it with the naked eye, and you need advanced methods to or microscopic techniques to actually view these particles. It's a multidisciplinary science, meaning that it does not only involve chemistry. There are biologists, physicists, medical experts, and engineers that they have all gained an interest in nanotechnology over the years. And what's interesting about these materials is you can control them at the atomic level to suit the specific application that you want to use them for. So where did it all start? Well, to many of us, if you look at the picture on the slide, it looks like a normal window that one would see in a church. But what we didn't realize is that this picture dates back to the Renaissance period. And the artists who actually made these paintings were not aware at that stage that the paints and pigments they used actually contained gold and silver nanoparticles. So nanotechnology has been in existence since the Renaissance period, only we needed more advanced and modern techniques to be able to identify the different types of nanostructures that exist out there. So one of the first types of nanostructures that were identified back in the 1980s were the fullerenes, which basically consisted of carbon atoms linked together in a soccer ball-like structure. And then when I joined Technikon Witwatersrand as a new lecturer, the hot topic of discussion was carbon nanotubes. Now these materials essentially consist of carbon atoms linked together in graphene-like units. You can get a single row of these units which make up single-walled carbon nanotubes and multiple layers which make up multi-walled carbon nanotubes. And you can see from the diagram they have a distinct tube-like structure. Okay, so various methods have been used to prepare these types of materials, but I'm going to focus a bit on hydrothermal synthesis this evening, largely because it's one of the emerging techniques that are used to make specific types of nanostructures. Now, the hydrothermal technique works on a principle where your substrate particles are soluble in a hot aqueous medium, and you can actually isolate different types of crystal structures from this technique. It works on the principle of a temperature gradient. So, and usually it's performed in a Teflon-lined autoclave reactor. So you have your warmer end of the autoclave reactor where your substrate dissolves in the medium, and then you have the cooler region where your crystal structures form. And what's interesting about this technique is you can control the temperature, the reaction times, and the pressure, and make different types of nanostructures. So in this slide, I'm showing you how we prepared some nitrogen-doped zinc oxide nanocabbages because they have a cabbage-like structure. And we did this by mixing zinc acetate with hydrazine. There was some stirring and pH adjustment involved, but to obtain the nanocabbages, we heated this in an autoclave reactor at 180 degrees. And I will tell you a bit later what application we use these nitrogen-doped zinc oxide nanocabbages for. On this slide, what you see is different types of nanostructured morphologies that one can attain using these hydrothermal techniques. You can see they vary from nanowebs to nanorings to nanorods, and the list goes on. There are a number of characterization techniques that have been used to characterize these materials. The most important has been scanning electron microscopy and transmission electron microscopy, largely because these techniques help you to identify the morphology of your materials. Okay, so these materials have a unique range of properties that have enabled them to be used in a number of fields, but I'm going to focus on the fields which myself and my research group have worked on quite intensively, and that is applications for water treatment and forensic applications. My favorite term for this is nanoforensics. So coming back to the South African problems that we're trying to solve in this research, what you see in this picture is still a familiar scene in South Africa where communities that live in rural areas are forced to go to a borehole or a well and collect water, and sadly that water isn't of the best quality. It's contaminated with various pollutants, and we are getting emerging new pollutants in the water every day. So this is one problem we're trying to address in our research, the poor water quality in South Africa. Then I'm sure many of you remembered the recent looting that took place in July. That was yet another criminal activity in South Africa. And so crime is on the rise in South Africa, and just like you get emerging new pollutants in the water every day, you also get emerging new crimes every day. So another problem we're trying to address is this issue of crime in South Africa. So how have we addressed it with the laboratory-based research that we've conducted till date? For the improvement of water quality, we've developed nanomaterials, nanostructured materials, and nanocomposite materials as adsorbents that can remove toxic water pollutants. We've also developed nanomaterials and nanocomposites or nanostructured materials that are effective as photocatalysts for degrading mostly organic pollutants, but that does not discount them from being used for degrading inorganic pollutants as well. And then to address the issue of crime, we've developed nanocomposites and nanomaterials that have been geared towards improving blood detection and latent fingerprint detection with a view to helping to make law enforcement officials' lives much easier. Okay, so coming back to the water treatment application, why have we chosen to work with nanosorbents specifically? Well, these adsorbents have very large surface areas which are favorable for adsorption. You can also modify the surface, add different functional groups, different chelating ligands that makes it more pollutant specific, so you can tailor make it to absorb a specific pollutant. They tend to interact with a number of reactive agents. And also, once the pollutant is adsorbed, it's easier to control and model the mass transport properties. Okay, so I'm going to start off by telling you about my journey in using nanomaterials for water remediation. This started off with my PhD studies, where I compared unfunctionalized, functionalized, and that was for the multi-walled carbon nanotubes, and activated carbon for chromium-6 removal. And what I found was the unfunctionalized multi-walled carbon nanotubes worked best for this purpose. They worked even better than activated carbon, which is a well-known conventional adsorbent. And they were very effective for the removal of even part per billion levels of this pollutant. The only drawback was there was some interference from competing ions, and this work was published in Journal of Hazardous Materials. As a follow-on study, I attempted putting sulfhydryl groups onto multi-walled carbon nanotubes for mercury-2 remediation. Now, the chemists in the audience will know why I did that, and that's because mercury's got a very high affinity for sulfur, so it's likely to interact with the sulfur on the carbon nanotubes and facilitate the adsorption. So this is the mechanism that we proposed. The sulfhydryl groups are expected to be acidic in nature, so you create sulfur centers that can bind to the mercury ion, but it was only a proposed mechanism at that stage. And some of the highlights of the study was we found that sulfur-containing multi-walled carbon nanotubes were very effective for the remediation of mercury-2. There was not that much of a difference with the performance of sulfur-containing activated carbon, but we found that it was highly selective in the presence of SO2, and that's where the sulfur-containing multi-walled carbon nanotubes outperformed the sulfur-containing activated carbon, and there was a definite chemisorption of mercury-2. This was work that we published in Microchemical Journal. Okay, then moving on to some further adsorbents that have been developed as I started my career as a postgraduate supervisor. And I'm going to tell you about a project which I co-supervised with my colleague, Professor Bianda. What we tried to do there was to develop a multifunctional adsorbent. Now, when it comes to water pollutants, you get three different categories. There's the inorganic pollutants, the organic pollutants, and the pathogenic pollutants, which are basically viruses and bacteria which can exist in the water supplies. So in the study, we tried to strategically develop a method that, a material that contains these different components to strategically remove the three kinds of pollutants. So the phosphorylated multi-walled carbon nanotubes were put there for removing inorganic pollutants. The beta-cyclodextrin was put there to remove the organic pollutants, and the chemists will know that these types of materials have a hydrophobic interior, which is good for absorbing organic materials via host-guest interactions. And then we put in a titanium oxide silver biopolymer for the antimicrobial activity. So the model inorganic pollutants that we worked with were cadmium-2 and lead-2. The model organic pollutants were trichloroethylene and Congo red dye, and we tested the antimicrobial activity on gram-positive and gram-negative bacteria. This to show you some of the results with the inorganics. You can see that the adsorption capacities were not that very high, but there was some adsorption observed via ion exchange and electrostatic mechanisms. For the organics, we saw a good percentage removal above 90%. Different mechanisms or interactions were involved, but what was of a noteworthy observation was the fact that the adsorption capacity for trichloroethane was far higher than that of Congo red dye. So it seemed like this adsorbent did work to absorb different categories of pollutants, but it had its own specific adsorbent preference for certain materials. And these are some unpublished results that I'm presenting to you today. But what you see from this data is that the full composite material containing titanium oxide and silver was necessary to inhibit microbial growth. And that was a positive sign to say that it can work for antimicrobial activity. The types of pollutants that we've worked with were not just necessarily metal ions and organics only. There's a lot of work that we've done on fluoride remediation, and there's just two studies in particular that I want to highlight here, where we basically decorated polyaniline nanofibers with a hydrous zirconium oxide material and also a hydrous binary oxide material for it to be effective for fluoride removal. Okay, so we've developed a lot of adsorbents, and they've been effective for a number of pollutants, but the question that often arises when it comes to adsorption technology is, what happens when the adsorbent gets spent? What do you do with it? And there's only two options here. One is to discard it, and then you're not really doing anything good for the environment. You're creating another environmental problem. So something else that's come into mind is, why not use the spent adsorbent in a reuse application? Okay, so we've tested the pollutant-loaded spent adsorbents for a number of applications. Unfortunately, I'm restricted with time this evening, so I'm only going to tell you about two such studies. The first of these was a study where we coated a carbon hybrid nanocomposite material onto coal fly ash, and we used that for cadmium-2 removal. And then we attempted using the reusing the cadmium-2 loaded spent adsorbent in a photocatalytic application, where we studied its potential to photocatically break down methylene blue dye. So this just, the picture in the slide just highlights to you how we prepared this carbon hydrogen nanocomposite, which was coated onto coal fly ash via a hydrothermal technique. And then we observed a reasonable adsorption capacity for cadmium-2 removal, but the highlight of the study was really it did work as a photocatalyst. We observed 97.41% degradation of methylene blue dye when we attempted reusing the cadmium-loaded spent adsorbent. Now, this has some new meaning for environmental remediation in that it can enable one to kill two birds with one stone. So you're creating your adsorbent that can remove the metal ion. Then once the metal ion is entrapped on the adsorbent, it can then serve as a photocatalyst to break down the organic material. Then in another parallel study, what we did was we cross-pollinated our water and forensic research. So we developed carbon dots, which we coated onto aluminium oxide nanofibers, and we used this for lead-2 remediation. And in our reuse application, we reused the lead-2 loaded spent adsorbent for latent fingerprint detection. So this just shows you how we prepared the carbon dots from waste banana peels using a hydrothermal technique. And then we prepared the aluminium oxide nanofibers via a simple sol gel technique. And the carbon dots were coated onto the aluminium oxide nanofibers via a simple adsorption technique. So again, you see a reasonable adsorption capacity, but again, the highlight was that the lead-2 loaded spent adsorbent was a good fingerprint detection agent. So this just shows you some diagrams in which we were able to capture the fingerprint images on different surfaces to prove that the presence of lead was significant in terms of helping us identify the fingerprints. Okay, so I've spoken enough about how we remove pollutants by adsorption. Now coming back to the nanocabbages, or the nitrogen oxide, nitrogen-doped zinc oxide nanocabbages that we prepared. We actually prepared this for a photocatalytic application. And we used methylene blue dye as our model organic pollutant. We found that it was highly effective for the removal of the dye. And we found that it was quite a stable and a reusable catalyst as well. Okay, so I've said enough about the water treatment applications. Now coming to the pure forensic applications that we've dealt with. What we did in one of our studies is we prepared nitrogen-doped carbon dots from potato peel waste. And then we also prepared zinc oxide nanoparticles using a simple sol gel method. And we prepared a composite material of the two by simple adsorption technique and used that for latent fingerprint detection. So some of the highlights of this study was that the composite material showed superior latent fingerprint detecting abilities as opposed to the base materials. Now what I mean by that is that the zinc oxide nanoparticles on their own and the nitrogen-doped carbon dots on their own were not as effective as the composite material. The fingerprint images could be clearly viewed under a live imaging microscope. And something else that was useful is that this material, or this nanocomposite material, was able to give us clear fingerprint images of aged fingerprints. Now that's important because sometimes crimes get reported after some days or months and you really need proper evidence. So if you can develop a material that can do that, it will really achieve great results. And that wasn't the only forensic application that we engaged in. We also prepared a bulb extract from a local plant known as Crinium macawane, and we prepared gold nanoparticles using this bulb extract and added those gold nanoparticles to luminol for blood detection and found that we got an enhanced signal. We also found that the Crinium macawane bulb extract could potentially mimic luminol in its function of detecting blood. And then further to the other work which we've performed on latent fingerprint detection, we also took waste coal fly ash, modified it with functional groups and coated dyes onto this. And we found that it was effective for latent fingerprint detection under daylight conditions. And this is something that law enforcement officials are really looking for because nobody wants to go out at night and shine a UV lamp just to find fingerprints. So this is certainly a material that could make the lives of law enforcement officials much easier. Okay, now looking at the forward of, or looking forward to the future of nanotechnology, and where will this research actually take us as far as product development, prototypes, and really solving real-life problems are concerned? Well, I really believe we started something here, and we need to start networking with engineers. Maybe there's a way we can use our adsorbent for on-site water purification, especially in rural areas. Perhaps one can come up with a nanoscale water treatment plant that can enable rural communities to have access to clean water. That's one idea that came to mind. The other idea is, what if we can develop smart nano sensors that can be embedded into water supply to help detect the presence of new emerging pollutants, perhaps in this 4IR regime, sorry, I beg your pardon. One can actually link it to an artificial intelligence system and track the release of pollutants. Then as far as the forensic applications are concerned, it would be nice to see if we could take the materials that we've developed for fingerprint detection and embed this into items that are of obvious attraction to criminals, like jewelry items, cell phones, and see if one could make a smart nanomaterial that can detect or distinguish between the owner's fingerprint and a criminal's fingerprint, and perhaps send data to the nearest police station to help the law enforcement officials perform their functions much better. I want to leave you with a thought-provoking question, and that is, we are living in this 4IR era where we often talk about robots, and nanorobotics is an emerging field. So can one create nanorobots then to solve South Africa's problems? I want to thank a number of people that have contributed to my research and my development as a professor. You can see my postdocs and students are at the top of the list because really they've been the frontline workers. It is their work which I presented to you today. So I thank my students for their hard work. I'd also like to thank my PhD supervisors for their valuable contribution. A special thanks to Professor Colville for being here this evening. There are a number of national and international collaborators that have added value to these projects, so thanks to them. My family and friends may not know much about the science of what I'm doing, but their moral support is sincerely appreciated. And if you're watching it online, know that I really appreciate you a lot. I want to also thank the CSIR for providing me with laboratory space and infrastructure when I needed it. To my colleagues in the Department of Chemical Sciences, thank you for your support, your moral support, and I have collaborated and co-supervised students with many of you, so thank you very much. I want to also thank the Faculty of Science for funding the postdocs and also for providing me with this platform to present my research. There were also a number of sponsors involved on this project. Eskom in particular supplied us with the coal fly ash that we've used in our studies, so thanks to them. And I want to thank God for my journey to professorship. I also want to pay a tribute to my late parents, who unfortunately are not here to see this, but they played an important role in my development as an individual, so I thank them as well. And thank you, the audience, for being here this evening. I wish everyone a safe future in these unprecedented times. And let's hope that nanotechnology can also provide a solution to ending this COVID-19 pandemic. Thank you.
Good evening, all. Professor Berger, Professor Tatum, colleagues, friends, faculty who are listening in tonight, welcome to the event. And it's my turn now to thank Kriveshini for her talk. When I was asked to give the response to Kriveshini, now Professor Pillay, I can call her that, following her inaugural lecture, it was just a given that I would come along and do this. I've known Kriveshini, Professor Pillay, since she registered to do a PhD at Wits, University of the Witwatersrand, 2007, I guess it was, when she started with us, myself and Professor Sukrowska. And what I liked about the project when Kriveshini, I'm going to call it Kriveshini, so I'm used to calling her, when she came to see me at WITS and talked to myself and Professor Eva Sukrovska, what I liked about the project was a cross-disciplinary project involving work from my own part, which is nanotechnology, and from Eva's, who was the environmental chemist. And so it was a nice combination of this project that allowed me to learn something about environmental chemistry as well. So it was really great to embark on a project of this type. Professor Pillay, Kriveshini, was what I call a gritty student. She was working at the time, doing a part-time lecturing. She was part-time lecturing at UJ while she was undertaking this study. And that requires a lot of resilience, determination to embark on something like this. Plus enthusiasm, because doing a PhD requires a lot of determination and grit. There are good days, but there are a lot of bad days when you do research. And she pulled through all this. And also the intellect to take on a new project and generate new knowledge. Of course, she succeeded. That's why she's here today. Since then, she's carved out a wonderful career for herself at UJ and has created her own research niche, as you've heard. She has succeeded in this academic environment at UJ. Over 50 publications, supervisor of the next generation of many chemists, attendance of many conferences, and so on. And that's the promotion of being made a full professor is a logical progression for her in her career. In today's talk, you heard about some of her activities. The title of her lecture was called Nanotechnology as a Tool Towards Solving South African Problems. An appropriate title given the University of Johannesburg motto, The Future Reimagined. And that fits in quite comfortably with that future at UJ. In her talk, she discussed two important problems facing South Africa, poor water quality and crime, and nanotechnology as a way going forwards with this, solving these problems. Nanotechnology is part of our future and fits in with the 4IR initiatives as one of the research drivers at the University of Johannesburg, so it's appropriate that she's involved with these topics. The talk showed that although she works in an academic environment, Professor Pillay's studies have an important and practical role in dealing with real South African social problems. So there's a strong link between academia and what goes on in the real world. In terms of the hardcore science that she spoke about, her interests relate to the removal of pollutants. We can think of metals in mine waters or the dyes, medicines that are disposed of by both industry and also you, the South African citizen. You're the ones who've got to look after your pollution as well. But that's her problem, is to try and, or that's her research direction, is to try and solve these problems. So what her studies have shown is that when you use various types of absorbents, you can remove these pollutants. But her studies have been investigating also the reuse of these materials, as she discussed, so that she absorbs the material and then uses those for future studies. But what for me has been interesting to see, because that's the sort of work I'm more familiar with what she was doing many years ago, is in this move into forensic sciences. Her career to date, with all her expertise developed at UJ, has allowed her to expand into this direction. It's a niche area well suited to her interests and capabilities, and I think it's a really good direction you've taken, Kriveshini, in that. So, in concluding, it's been a pleasure to have been connected to Professor Pillay over these many, many years. To see her blossom as a teacher, researcher, has been my pleasure. And my wish now is for her career to continue to blossom and lead to further successes and achievements in the years ahead. So, congratulations, Professor Pillay. Thank you.
Thank you, Prof. Andre. If you can come and assist us. Thank you. Thank you. Righto. Also pass you here. I so wish we had the full audience here this evening. You know, with all your staff and in the department, but also in the rest of the faculty, your families, your friends, because we would have liked to give you a proper applause, because that's what you deserve. So well done to you. And thank you for sharing your journey with us, Prof Pillay. It's a journey that I know of, because we go back also a couple of years, same as Prof Kowal, and I'm so proud of you, really. You know, I always regarded you as an excellent lecturer, someone takes her teaching so seriously, and as you've developed now also an excellent researcher, you know, and as also excellent supervisor. So you are really an absolutely example to younger staff coming through now, and I'm so happy that I can share in this moment with you. It was a fascinating, fabulous lecture, and I enjoyed it tremendously. So all the best to you in your future endeavors. I hope and I know that your research will only grow, and your research team, and I'm looking forward to see, you know, what is the impact of all these research that you've described. It's absolutely relevant, and I'm sure that we're going to use it in future to also assist this nation. So thank you very much, and congratulations once again. Then I also want to say thank you to Prof Kowal for that excellent response. Prof Kowal, you have been a mentor and the inspiration to many of the academics here in chemistry at UJ. We are neighbors, and we always appreciate what you've actually done for our academics here in the Department of Chemistry at UJ. So it's always good to see you, and I really thank you for also making this day even more special for Kriveshini by being here. So then this brings us to the end, and we just want to say thank you for joining us online. We hope that you've enjoyed this just as much as we've been enjoying it here sitting in the room. And yes, and we hope to see you very soon again for another professorial inauguration. So thank you. Take care. Bye-bye.